Hello everyone, welcome to Lab 6. Today we will learn about the analog to digital converter. Okay, so what is the analog and digital? You have learned some basic idea in previous lab. Now you will learn a bit more about it. So you can see that the microcontroller cannot read the analog values. For example, it cannot read 1.98 volt or 3.457 volt or 4.123 volt, something like that. The microcontroller only deals with 0 and 1. It understands just the digital number 1 or 0, that's all. So you can see here we have the signal of the analog from 0 volt to 5 volt, something like this. And the microcontroller will convert the analog signal into the digital signal. For example, if we have 1 bit, that means we only have 2 states, 0 and 1. When we transfer the analog signal to the digital signal of 1 bit, we have signal like this. And if we have 2 bit, so if we have 2 bit, that means that we have 4 levels, 0, 1, 2, 3. And we have the combination of 2 bit, you can see here, 0, 0, 0, 1, 1, 0, 1, 1. So we have 4 levels. From this analog signal, we can transfer to 2-bit signal like this. And if we have more bits, for example 3 bit, we have totally 8 levels, 0, 1, 2, 3, 4, 5, 6, 7. And this is the combination of 3 bits. For example, we have 000 here, 001, 010, 011, 100, 101, 110, and 111. So we have totally 8 levels. The signal will be better like this. And if you have more bits for the digital, you will have more accuracy. In this, we have 4 bits. That means that we have 16 levels from 0 to 15. And this is the 4-bit digital from this analog here. So we can conclude that if we get more bits, we can get more accurate reading. In brief, the microcontroller cannot read the analog, so it has to transfer the analog to digital. And the more bits, we get more accurate. So that is why we have the ADC. Now let's see, in the Arduino we have 10-bit ADC. That means we have 1024 levels from 0 to 1023. We have a 10 number of 0 here, and in the level of 1023 we have a 10 number of 1 here. So this is 10-bit digital. It will be like this, and you can see that we have the value from 0 volt to 5 volt, 0 volt for 0 and 5 volt for 1023 here. So 1023 here, it means 5 volt, and 0, that means 0 volt. So I can give you some example. If you read the digital of 0, that means it's 0 volt. If you read the digital of 1023, that means 5 volt. If you read the digital value of 205, that means 1 volt. 512, you have 2.5 volt. You have 675, you have 3.3 volt. If you read the digital value of 818, you get 4 volt, something like this. And this is the formula to translate the digital value into the voltage. So you get the digital value multiplied by 5 volt and divide by 1023. So let's start with the first experiment for today. So first we will connect the circuit like this. You have 5 volt from Arduino and ground to the demo board, and you have the port here. Port for the potentiometer. Connect the port to the pin A0 here. The purpose of this experiment is to read the voltage of the port and output the result to the serial monitor. And the port is connected to the pin A0. So I will connect 5 volt from the Arduino and the ground. This is the first step for every experiment. Next, we connect the port from demo to the pin A0. So the port here is in the third position to A0 here. With the version 2017, it have the bit different pin here, so be careful. After connecting like this, we will run the code. So the code here is already written for the analog read serial. So go to the Arduino, open basic analog read serial. So you see the code now. And then when you already connect the Arduino to your laptop, upload it. Finish. Okay, so now open the serial monitor, and the baud rate here is 9600. So change to 9600 here, and then you can see the value. It's now reading 866. So now let's see. When I dial this potentiometer here, you can see the change of the reading. So when I dial it counterclockwise, it now go back to 0, and then if I rotate it clockwise, it increase the value until 1023. So 1023, that means you get 5 ohm at the output, and 0, that means you get 0 volt. So try and observe the result. Okay, something like this. And then you can see the result in either the serial monitor or the serial plotter. So how to open the serial plotter? Go to Tool and go to serial plotter. Open this. First you have to close the serial monitor. Then go to Tool, go to serial plotter here, and you can see now it is plotting the value. And then when you dial the potentiometer, you can see that now the value is dropping. So I increase it. So if you go highest to the 1023, decrease it, increase, decrease, increase, decrease, something like this. So there's a two tools for you to see. The first for the serial monitor, the second for the serial plotter. It depends on you. In the serial plotter here, you can see it visually when it increase or decrease. For the serial monitor, you see exactly value. So I turn up the serial plotter and I turn on the serial monitor again. Show the value from 0 to 1023. So we finished the first experiment. Now let's analyze the code. Okay, close it. So this is the code for the analog read. I already have the similar version of this. So close this, open the desktop ADC. The code is very simple. You can see in the first, we just use the serial begin at 9600 as previous. There's nothing new here. This is the bring out the result, bring out the sensor value. This is not new. We have the variable of sensor value is an integer, and you're expecting the sensor value it will have the range from 0 to 1023. The only new thing here is that you set the sensor value equal to the analog read of A0. That's all. So very simple. You can see that we have the review of previous lab. We have the digital write and digital read. For the digital write and digital read, you need to define the pin is an input or output. For example, for the digital write, you have to put the value of the pin here and you say output, and you use the function digital write. You put the value of the pin here and you put the value of high or low. For the digital read, you do the same thing. You have to define the pin as an input. This is the value of the pin here, and you use the digital read and put the value of the pin here. For the analog read, you don't have the pin mode. You just use the function analog read, and remember to put an A before the number. In this experiment, we use the pin A0. So you have to put A here and put 0 into it. We don't have the pin mode for it. Why? Because you remember the Arduino pins. For the digital pins, the pins can be either input or output. But for the analog, it only input. So we don't need to define the pin mode for the analog. When you see the Arduino board, you can see here it say analog in and they say A0, A1, A2, A3 to A5. In the digital, we just use directly the number from 0 to 13. So next, you can see that we have already read the value from 0 to 1023. Now we want to change to the voltage. So come back to the formula here. If we want to change the digital value into the voltage, we use this formula. The voltage equal to the digital value multiplied by 5 and divided by 1023. So now let's do it. Okay, so now you can see the voltage value. Okay. Voltage value equal to the sensor value multiplied by 5 divided by 1023. So because the voltage value will be 1.25 something like that, or 3.6 something like that, the type of this value should be float. So the float voltage value, okay, and then you run it, upload the file. So I forgot to change this to the voltage value, and upload it again. Okay, done uploading. And then open the serial monitor. It will show up 1.00. So now let's see when I change the dial. So it will change from 0, 1, 2, 3, 4, or 5. You just see the integer value. So how to see more accurate value of the reading? So you have to do one more thing. Close this. Go back to the code. So remember to put 5.0. So when you put 5.0, it doesn't change anything, but it will make the voltage value will have the float type and it will show more digit value. So now just run it and upload it again. Done uploading. Open the serial monitor. And you can see now we get the value. For example, here we see 3.76. So now when I reduce the voltage, rotate it counterclockwise, it's now 0. Increase it. We get 5 ohm. Okay. So this is how we read the voltage by the analog read. So now close it. Okay, just show up like this. For the analog read, if you want to read the voltage of the pin, you just have two new things. First, you need to define the variable as a float. It will have the value from 0 to 5 ohm. And then we use the formula of the sensor value multiplied by 5 and divide by 1023. And remember to put 5.0 to get the exact value of the voltage. Okay, very simple. Next, so now we try to read the temperature from the sensor TMP36. So the TMP36 here is just a temperature sensor and output the result to the serial monitor. The TMP36 will connect to pin A0. Okay, so now we change the pin to TMP36. Yeah. Okay, and we have the pin A0 as previous, so we don't need to change. And then move next. So let's learn a bit about the TMP36 temperature sensor. You can see here, this is the TMP output voltage, and this is the temperature. When the temperature rises, the output voltage will increase. So you can see the higher temperature, you get higher voltage. And this is the formula of calculating the temperature from the voltage. So if you know the voltage of the TMP36, get this value and you minus 0.5 and take all it multiply by 100. For example, if you read the voltage of the TMP36 is 1 volt, now the temperature is equal to 1 volt minus 0.5 multiplied by 100. Equal to 50 degrees. So let's see here in the chart, you can see the voltage here from 0 to 2 volt. When you get 1 volt here, at this point, it is 50 Celsius degree. Okay, so let's start. So this is the code of reading the temperature. We had the same code of the previous experiment. So just run it and see. Open the serial monitor. So we get the voltage now up 0.65 volt. And then I will apply the formula here to read the temperature. The temperature should be a float value. So I say just temp. And I say temperature equal to, we have the voltage minus 0.5. We have the voltage value here. Voltage value minus 0.5 multiplied by 100 and close with the semicolon. I want to bring out the temperature. Let's run it, upload it. Okay, done the plotting and open the serial monitor. So what you see now, we read the temperature up about 14 to 15 Celsius degree. Okay, so now in my room it's 14 degree, and I try to touch the temperature sensor because my body is 37 degree. So when I touch the temperature sensor, the temperature increase. You can see now it is 16 degree. Can it increase more? Okay, about 17 degree now. And then when I release the temperature sensor, I'm expecting the temperature will drop back to about 14.5 degree. So now the temperature is dropping. It's now 15.5 degree. Okay, so that's the code that you use to read the temperature. In your home, you can use the hair dryer or something like that to make it a bit hotter and see the results. Okay, now let's see the code. The new thing here, we have the temperature is a float type, and then you apply the formula temperature equal to the voltage value minus 0.5 multiplied by 100. That's all. So now let's move to the LDR. In the demo board, we have one LDR here. So what's LDR? LDR is a light dependent resistor. It's only the resistor, but the resistance can be changed by the light. This is the symbol of the LDR. Some people use this, some people use this, but they are the same. Resistance of the LDR here depends on the light, and when you get brighter light, it's a lux here, that means the illuminance. Higher lux, that means we get brighter light. Lower lux, that means you get very dark light. The brighter the light, the lower the resistance. And in the demo board, we connect the LDR in series with a 4.7 kilo ohm, and we connect it to 5 volt and ground. We will read the output voltage of the LDR here. You can see that when we get higher illuminance, we get lower value of the resistance of the LDR, and as a result, we will get lower voltage of the LDR. So now let's connect the LDR to pin A0. We already connect the pin A0 here. We just change to the LDR. So our task is to read the light sensor and output the result to the serial monitor, and the LDR is connected to pin A0. Now let's run it, and you can see that this is the code that we have used in the analog read. So I delete 2 lines here. I delete this, and I want to bring out the sensor value. Okay, so now upload it and see. Open the serial monitor. Okay, now you can see that we are now reading the value of 840, something like that. And then when I cover the LDR, you can see it's increased to 973, something like that. When I remove my finger, it will decrease to 848, something like that. So now let's make the LDR a bit brighter. I have my phone and I have the light from my phone. So I cast the light to the LDR. Now we're reading the value of 120, something like that. So make it closer. So when the LDR gets very bright, it gets very low value. You can see. So now we get about 45 when I remove my phone. The voltage now come back to 800, something like that. Okay, turn it off. Come back to the lecture. I use the same code of the analog read, and you can see it changed the value of the voltage output. And let's say try to cover the LDR with your finger or shine a light from your phone to LDR, then observe the result in a serial monitor. You have seen that? Okay, move next. So now we try to control LDR. This is just a very simple application of it. We have one LED here, and it will cast the light directly to the LDR. I want to read the light sensor LDR here and turn on the LED when the LDR is at low illuminance. So when the LDR is very dark, we turn on the LED. So to turn on the LED, you need to use the digital write to this LED. So you connect the LED here to pin 12 or any pin here. In this experiment, I want you to connect to pin D12. Okay, so let's do it. I already connect the LDR to A0. So I will connect the LED here to pin 12. So now let's see the code. So the code here, I say if the sensor value is larger than 500. When you read the value of very high, that means the illuminance is very low. If the sensor value is larger than 500, we turn on the LED. If no, else, that means the illuminance is high, you turn off the LED. Okay, so let's make the code. So this is the sensor value we read from A0. If sensor value larger than 500, so we turn on the LED. Digital write. We digital write to pin 12 and high. Else, and we digital write a pin 12 low. Okay. Before using the digital, you need to define the pin D12 as an output. Pin mode, pin 12 output. Okay, that's all. So now let's run it. I turn on the camera already. Move the code a bit in the left, upload it. So now the LED will turn on the light to make the LEDR very bright. Open the serial monitor. It's showing 500 and 100, 530 something and then 130 something. And the LED will turn on, turn off very quickly so you don't see the change in the camera. So I will make it a bit slower by a delay. So I want to make it a bit slower so I can delay maybe 500, something like that, and see if you can see the change or not. Yeah, so you can see the change now. When the LED turn on, it will be 120, something like that. When the LED turn off, it will be 800. So it will turn on again to cast the light to the LDR to make it brighter. So in the case that I cast my light from my phone to the LDR, so now the LDR is reading about 100. So that means that the LED will not turn on. When the value is very low, that means we get very high illuminance for the LDR, so the LED will not turn on. And when I remove my phone, the LED will turn on. Okay, so I can make a bit delay, a bit longer, about 2 seconds, something like that, 2000. Upload it again. And open the serial monitor. At the moment my room is very dark, so we get very high value of 860, and then the LED will turn on to make the value lower to 120, the LED will only turn off when it gets very high light density. So now the LED is now turned off because I cast very shy bright light into the LDR. This is very interesting. Now turn off. Okay, that's all for today. The only new thing that you have learned is to use the analog read. So remember to put an A before the number of the pin. And if you want to change the analog read to a voltage, use this formula. Voltage equal to the analog read multiplied by 5 divided by 1023. Remember that to put 5.0. Don't put 5 to get the correct value of the voltage. And you also know how to use the temperature TMP36. And if you want to change the TMP36 voltage to the temperature degree, use this formula. The Celsius degree will equal to the voltage minus 0.5 multiplied by 100. And you also learn how to use the LDR and apply it to some basic application. If you get very high luminance, you get low resistance and low voltage value. Okay, and you also know how to read the analog read from the port. This lab today is very simple. Okay, remember to download and finish Lab 6, and before that, spend time to review your Lab 5 solution and compare to your report. And if you have any question, please post it on Canvas discussion. Thank you very much and goodbye.